So in this unit, we're still talking about quantitative data, but we're going to talk about a couple of different types of measurements that answer the question, where is a data value in a distribution of a whole bunch of data values? We've talked about the center, we've talked about the variability, we've talked about potential outliers and how actually to calculate outliers. But we haven't really talked about the location of data values, and that is actually helpful because it answers a lot of questions like this. So we have two guys here. One took the SAT, scored 1,050, and then Guy Fieri took the ACT, scored a 23. Two different college entrance tests. And the SAT is out of 1,600 possible points, and the ACT is out of 36 possible points. So what we want to do is we want to try and compare the two and answer the question, who had the better score? Any ideas on how we could do that right now? Yeah, find the percent each one got? Sure. So Young Saver got 1,050 out of 1,600, which converts to about 66%. And Fieri got 23 out of 36, which converts to about 64%. So one could make the argument that Young Saver did better on his entrance test than Fieri did on a different one. Okay. But it doesn't really, like, there's other factors at play that make these values not very accurate. Okay, because it all depends on, like, how did everybody else do on that SAT? How did everybody else do on that ACT? And one way we can measure that is something called a percentile. And a percentile represents the percent of data that is less than or equal to a certain data value. So it's kind of like saying, where do I stand in a group of data values? Where does my score stand? Or where does my value stand? Before we go back to the SAT and ACT, we've seen this example before when we were talking about measures of center and measures of variability about yearly salaries, 12 yearly salaries of employees at a company. And we want to find what percentile is the person who makes a salary of 43,000. So what we need to do is we need to find, where is that person's data value? Where do they rank out of the total? And we do that by listing all the data values in order, and then counting all the data values that are at or below 43,000 and putting that over the total data values. So here's 43. So the number of data values that are 43 or below is 10. Out of the total number of data values, which is 12. So to find the percentile, we would do 10 out of 12 and round it to the nearest whole number percent. Okay? And we would get approximately 83%. And the way that we state it is we say this salary is at the 83rd percentile. That doesn't mean that they scored 83%. It doesn't make sense for salaries. Okay, it means that their value is the same as or better than 83% of the salaries at this company, or of at least the 12 that were measured. You're already familiar with some percentiles, we just never referred to them as percentiles yet. When we were looking at box plots, remember, the box portion of the box plot, the left-hand side of the rectangle is the value of Q1. The vertical bar somewhere inside the rectangle is the median, and the vertical bar on the right side of the rectangle is Q3. So what percentile would Q1 be at? 25th, right? Because 25% of the data values are the same or below. So this would be 25th percentile. And the median? 50th. And Q3? 75th. Good. So let's return to the two guys that wrote the college entrance tests. And the year that they wrote, here are the percentiles for various scores. So you can see the SAT scores here, it gives the corresponding percentile, okay? Obviously, if you scored 1600, you're at the 100th percentile, because that means your score is the same or better than 100% of the others. You don't say your score is 100%. You say your score is at the 100th percentile. Okay, just like 1550 doesn't mean that you scored 99.3%. It means your score is the same or better than 99.3% of all the people that wrote the SAT. So let's compare their percentiles of the two. Remember, Young Saver got 1050. So Young Saver is at the 45th percentile. Whereas Thierry remember, he scored 23. He's at the 69th percentile. That suggests that Fieri did better on his than Young Saver did on his. Okay. Going better because it's 5 percentile. Because this is taking into account the percentiles, how everybody else did. When we just found the percent each one scored, we were just finding how they did. Okay? And we can graph percentiles, we can graph situations like this using what's called a cumulative relative frequency graph. And it usually takes this kind of curvy shape. And we start at 0 because the lowest value will be at the 0 percentile. And it goes all the way up to 100% because the highest value is obviously going to be at the 100th percentile. So this is a cumulative relative frequency graph of the ACT scores. So you can see you can look at the graph here and you can get a whole bunch of information from it. I mean, 10 is at the 0 percentile. So that must have been the lowest score. 36 is at the 100th percentile, obviously. We can see Fieri's score if we just go to 23 and go up here, and we can see we're at about 69. What about a score of 18? So we want to get its percentile to determine whether it's actually a good score. So if we go up here, it looks like we're at about the 40th. How would you describe that? Below average, not great. Okay, I mean, not terrible, but not great. Whereas if we looked at Fieri's score at the 69th percentile, we would say, yeah, that's pretty good. Because that's getting close to the same as or better than 3/4 of everybody who wrote it. And a lot of people write these things. Second question, you're applying to an elite college and you want to score in the top quartile of test takers. What score do you need? What would be the percentile of the top quartile? 75th, right? So we need to find the score at the 75th percentile, which means we've got to go the other way now. We've got to get to 75 and then come over to where the graph is. Looks like we're about 24. This is assuming that you don't have this table to read from, that you only have a graph to read from. So approximately. So that's one way we can describe location. It's using percentiles. There is another way to compare, and that's by standardizing their scores or calculating a standardized score. So what we're going to do is we're going to equate the two tests. And how can we do that? Well, we can describe how each test score, if I'm using the ACT, SAT example, how many standard deviation it is above or below the mean. And that's called a standardized score, or what we call a Z score. So what we do is we do a certain calculation that tells us, okay, how many standard deviations is this data value above or below the mean? And to do that, we take whatever the data value is, we subtract the mean of the distribution, and then we divide by the standard deviation. That tells us how many standard deviations a data value is above or below. If it's above, the Z score is going to be positive. If it's below, the Z score is going to be negative. And then this is just the fancy notation we use. This represents a data value, xi. This represents the mean of the entire population. So that's why we use the Greek letter and not that X bar. We use X bar to represent the mean of a sample, not everything. And we use this lowercase sigma to represent the standard deviation of the entire population. Whereas we would use S of X if we talked about a sample. Yeah.
You said if it's above the tongue, it's below, right?
Yes. Okay. So this is just a little blurb on why the standard deviation matters, why we can use it to compare scores of different distributions of data values. Okay. So imagine that this young Saber guy who apparently likes to play basketball, when he was in high school, scored an average of 14 points per game. And then we've got a distribution of the points per game of two leagues. League A players average 10 points per game. And they have a standard deviation of 2 points per game. League B also has an average or mean of 10 points per game, but with a higher standard deviation. Okay? So that means that in League A, remember he scored 14 points per game. He would be about here. This represents all the data values. His is about here. His points per game is the same as or higher than pretty much the rest of the data values, with a standard deviation of 2. But a standard deviation of 4, okay, his score is here. He's not doing quite as well in League B. He's still above the mean, but we can see that there's a bigger chunk, because you got to imagine all of the data values are in there for everybody in the entire league. And it forms kind of a bell shape, which we'll talk about later in this unit. So in this one, not many had higher points per game. But in this one, more, a greater percentage had higher points per game. So he did better in League A when his standard deviation was 2 points per game. Okay. So we would say his performance is more impressive in League A. Because there is less variation. Okay. Fewer players have higher points per game than him. So when we calculate Z scores, or when we standardize scores or data values, okay, a point's location in the distribution depends on both the distance from the mean and the distribution variability or spread. That's why standard deviation matters. It's a good way to compare different distributions. And another example of that would be, you want to talk about who's the best basketball player of all time. Okay. Well, it's kind of hard to compare because you've got really good basketball players in different eras. So you've got a guy, Will Chamberlain, in the 60s. Okay, that's when he played. He was averaging 30 over 30 points per game. And then you've got Michael Jordan in the 90s was averaging the same. And then you got LeBron in the last decade who was averaging 27.1. Well, one would look at these and say, okay, well, clearly Wilt and Jordan, were performing better than LeBron. But it all depends on how everybody else did in that era. Okay, maybe these were high scoring eras and their scores aren't actually as high as the rest of everybody else. Maybe this was a lower scoring era. That's important in order to compare, which is why we standardize. So in order to standardize, we need to know in each of these eras, what was the average points per game? And we can see in the 60s, it was high. And then it came down in the 90s and down even more in the 2010s. And the standard deviation, there was more spread in the 60s than there was in the 90s. And there was more spread in the 90s, a little bit more than what there was in the 2010s. So in order to put all this information together, if we want to make a conclusion to say who's the best, we calculate their Z-scores. So for Wilt Chamberlain, we're going to take his points per game, subtract the mean, and divide by the standard deviation. And when we do that, we're going to get 2.8. Remember, that's 2.8 standard deviations above the mean because it's positive. So clearly he's doing better than the average player in the 1960s in the NBA. Jordan, 30.1 minus the average points per game in that era of the 90s, divide the standard deviation in that era. And when you do his, you get 3.6 standard deviations. So he performed better in relation to all the other players in the NBA during that era than Chamberlain did during his era. And we can see that kind of makes sense because even though they have the same average points per game, the points per game, the mean was lower, as well as the standard deviation. And finally, LeBron, 27.1, minus the mean in that era of 8.4, divide the standard deviation, gives us 3.4. So we can look at his and say, okay, even though he had fewer points per game than Wilt Chamberlain in the 60s, he actually did better in relation to the other players in those eras. So if we standardize their scores for their points per game, we could possibly make the conclusion that Michael Jordan is the best. Let's see what a negative looks like. Let's look at a guy who didn't have that many points per game. Okay, guy named Adam Morris. He averaged 2.2 points per game. So his Z-score would be 2.2 minus 8.4, divide 5.5. This is also in the 2010s. Okay. Get to this. Negative 1.1. And remember, this would be standard deviations below the mean. Yeah.
Is that like a, you wanted to write SCD to UBS, like, things like that abbreviated for?
I'm okay if you write it abbreviated. Or if you write it out, that's fine too. Yeah, it's up to you. Okay, so just to wrap up the Z-scores. If the data value is greater than the mean, the Z-score is going to be positive. If the data value is less than the mean, the Z-score is going to be negative. And we've already talked about if it's a positive Z-score, it's above the mean. If it's a negative Z-score, it's below the mean, just to sort of summarize that. One other thing I want to add is just go back to this page. We don't really use this piece of information a lot, but it is kind of good to know. So when we standardize a set of data values, we're creating a new set of data values, aren't we? Like how many like we're going to have numbers like 3.3, which represents above the mean. We're going to have negative 2.1, which represents below the mean. We're going to have a whole list of Z-scores. If you were to take all those Z-scores, if you were to calculate the Z-score of every data value in a distribution, you'd get a new distribution. Okay? And that new distribution, or the distribution of Z-scores, always had the mean of 0 and a standard deviation of 1. Because if you think about it, the mean is going to be 0 because when we average out all the ones above and below, it's going to be nothing. And then if we calculate the standard deviation, it's going to work out to be 1. We use this piece of information when we talk about something later in this unit. We used to use it before graphing calculators. Because before graphing calculators, you had to use tables that had a whole bunch of numbers. Just like before scientific calculators, when you guys did trig, or when we did trig, we had to look up all the answers on a table. Right? You couldn't do it on your calculator. So if I wanted to find the sine of 46 degrees, I'd have to go to this big table and find, okay, 46 sine 0. Yeah. Okay. Okay. I think we'll leave it at that because we really talked about this.